Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JIF 318 Quantum Mechanics. We are in chapter 3, the Schrodinger equation. In this segment, unit 3.4, we will discuss the derivation of the Schrodinger equation. If you notice here that I put apostrophes on the word derivation because actually Schrodinger equation is not was not derived from any other mathematical operation, but it's actually just an inferment. Later we'll discuss how he inferred from the relationship of total energy equal to potential energy plus kinetic energy. So it's not exactly derivation in a purely mathematical senses. Okay. So the objective of this lesson is that we hope the student will be able to describe how Schrodinger arrived to his equation or how he derived, how he come to bring out the equation which bore his name, Schrodinger equation. So again, derivation, question mark there, is it really derivation? I'll let you judge later after this segment. So we intend to derive an equation which corresponds to the total energy, and for non-relativistic situation, can say that the total energy is equal to the kinetic energy, which is P squared divided by 2m, where P is the momentum. So applying the momentum operator twice, in the previous segment we had discussed how we can derive the position operator, momentum operator and energy operator. Okay, so the momentum operator is basically negative I h bar nabla psi equal to p psi. But now if we apply it twice, basically we multiply it. So on the left hand side, we have negative I h bar nabla or del multiplied by again by itself multiplied by psi equal to dot product of momentum multiplied by psi. So what we have is negative h bar squared del squared psi, the wave function, equal to p squared psi. Okay, it is just a recall what we mean by del or nabla squared equal to nabla dot product of nabla. Then basically the differential there is just the second order differentials. Okay, dividing both sides with 2m. Okay, we have those, then we divide by 2m. Why we want to divide by 2m? Because on the right hand side we have p squared, momentum squared, but to relate it to energy, it should be p squared divided by 2m, so that we get this E. Okay, because in the previous slide we have this relationship E equal to p squared over 2m. So when we have this relationship with p squared here, in order to relate it to energy, it should be divided by 2m. If you divide the right hand side with 2m, then the left hand side also you should divide by 2m. Then we can replace p squared per 2m with E, and then we know that E is related to energy operator I h bar delta divided by delta t. So now the wave function psi satisfy this equation. Okay, we have the relationship now in terms of the energy operator. Okay. Unjustified. I use the word unjustified because it's not exactly uh, justified in the sense that it is something like out of the blues. Not exactly out of the blues, but uh, this is the proposal by Schrodinger. What happens if we now add a potential energy B to the system? Just now we have this the equation without V but containing the energy operator. Okay, when we look at classical mechanics, the total energy is the sum of the kinetic and potential energy. Okay, so this is the kinetic energy, this is the potential energy. So why not like the classical mechanic, we have total energy equal to potential energy plus kinetic energy. Then why not we derive or have one formula with the term potential here? So basically, there is no some sort of like no reason or there is no way we from a mathematical operation to put V there. But just by comparing with classical mechanics, total energy, there is a potential energy there. So Schrodinger add plus V psi there. That means the V here, potential energy, was added so that it looks similar, or what should I say, in the same form as the total energy uh, in the classical physics. Okay. So here we are talking about E on the right. So on the left hand side, just add the term B. Of course, you multiply the wave function psi lah. Something like that. I mean, it is out of the blues. So I say that's why the question is whether actually he derived the equation. No. Is it justified? Actually, no. But for the sake of some sort of like similarities with classical physics, there should be a potential there. So the previous equation can be modified. So it is just modified accordingly by adding V here. That means the potential. So this is the Schrodinger equation. Basically, this is the backbone of quantum mechanics. And actually, if we look back, the term containing nabla squared and the term containing all these are operators. Okay, on the right hand side the energy operators, on the left hand side is the momentum operators, and momentum you can see here is in the kinetic energy system. We have P squared. Okay, so basically if you have the kinetic energy part in the Schrodinger equation, then we should also have the potential energy part. That's why it is put there. The V actually was being put there just so that we have similar form of total energy. Okay, this is the operator for energy, E with a cap there. Okay, so this is the Schrodinger equation. I hope you memorize this equation and you know what it means. And in fact, from the objective of this lesson, you should be able to derive or describe how Schrodinger Schrodinger managed to introduce this equation. Okay. So this is Schrodinger equation, possibly the most important equation in the 20th century physics. Yes, because most of the discoveries in atomic physics, in nuclear physics, and in particle physics due to this equation. So actually we have not derived this equation in a mathematical sense. It's just to the idea come that if in classical physics you have total energy as the summation of potential plus kinetic energies, then why not in quantum mechanics? However, you can see that psi satisfy the equation if v equal to 0, because initially v was not there. Okay, when we show the first equation here, when we get the initial form of the equation, we say that wave function psi satisfy this equation here without any potential. But when we put b in there, then psi basically does not satisfy the equation with b. Because if b is not 0, psi will not satisfy it. That means it will not satisfy the equation. That is, you cannot solve the equation. Okay? Because the initial form without the v actually satisfy the equation, but suddenly you put v, and if v is not 0, of course, psi will not satisfy this equation. Then Schrodinger have to put forth a postulate. Postulate, that means his idea, just like the Niels Bohr postulates and Planck postulate. Actually, postulate is something that being put forth, which is difficult to prove, but it agrees well with experimental values. Okay. So this equation will give the correct wave function psi for any potential v. That means not only 0. Just know that the condition for psi to satisfy the equation, v should be 0. But Schrodinger put forth his postulate that actually it will satisfy for whatever value of v. The prediction of Schrodinger equation do agree with a wide variety of physical phenomena. So even though scientists were reluctant to accept his ideas, but when they check it out against experimental data, they found that yes, Schrodinger equation with v inside it for any value of v do agree with a wide variety of physical phenomena. So basically, we have to accept that Schrodinger equation is correct, even though we need the derivation of the equation is a little bit some sort of like questionable. Okay. In its most general form in 3D, okay, if it is in 3D, of course you have the x, y, z and time. Okay, so you extend or expand this into the different component, delta x squared, delta y squared, delta z squared, and also the v there, everything in 3 dimensions, including or in addition to time t. In 1D or one dimension, it's a little bit simple because we have only x, so it's a little bit simple. And most of the problems or question in the exam, most of the time it is in 1D. But from there you can expand it to 3D. Okay. So if it is in one dimension, negative h bar squared per 2m, delta squared psi per delta x squared plus b psi equal to I h bar delta psi per delta t. So this is the Schrodinger equation in one dimension. In conclusion, Schrodinger equation was not derived in a mathematical sense. Schrodinger had to propose a postulate so that the wave function psi, the wave function psi can satisfy his equation or can satisfy the Schrodinger equation. Fortunately, his equation do agree with a wide variety of physical phenomena. That's why we have to accept his equation and we have to study that. I mean, it becomes a basis for quantum mechanics. Thank you for your attention.